Please bring your ID card. Okay, we're gonna start in about 5 seconds. Okay, you ready? All right. Okay. Good morning, everyone. Any question for me about the deadline extension? None of you get any extension, okay, unless you have the university skills. When you have the university skills, even though this deadline gets extended, the next deadline stays the same unless you have the university skills during the time that the homework is assigned. Question? Yes, sir.
Yeah, so do we have to resubmit homework one if we didn't put a picture with it?
Yeah, put a picture on it. Yeah, let's put a picture on it. That's the first question, so that I remember which student. More question for me? No more question for me? Martin, where's Martin? Martin Walker. Not here? Oh, okay. What did we learn last time? You remember? What did we learn last time? Yes, sir.
Can you go over a question from the homework?
Question on the homework. There's a solution. There's a solution uploaded. Let's not do it today, okay? We will try to do it next time. How about that? How many people that have some problem with the solution that's not clear? Or you haven't taken a look at the solution? Okay. So if there's just 1 or 2 or 3 students, let's do it in my office. But if there are many of you, we'll do it here. Let me ask you again next time. Okay, Marty, what did we study last time? Emotion. What else?
Separation, how to read the charts if they're not conventional or at the...
Do you know how to use those separated equations?
Nope.
Why not? How many equations that you need? I think there are horizontal equation, gas capacity equation for horizontal separator. Okay. Liquid capacity equation for horizontal separator. Okay, those 2 equations. And gas capacity equation for vertical separator. Liquid capacity equation for vertical separator. And the retention time equation that have 1440. It's about 5 equations, is it, Martin? Yes? So just use 2-3 of those. We will be able to size the separator. But you can use the chart, right? Chart is okay. Okay. Chart doesn't give more point on the exam, even though it's 90% of the time you will have to use the chart. On the exam there will be some calculation. For sure, we will need to be able to tell what is the retention time, how much. If I have the size of the tank, I do have full, how much is the retention time do I have? Alright? So you have to be able to calculate volume. What about heater treater? What do we learn? Okay. Zach, what did we learn for heater treater?
What do we learn about heater treater?
Yeah. Did we learn about heater treater? Yeah. Do we talk about equation on heater treater? Yes. How many equations do you need? Several? Oh. Alright. Heater treater. First, The theory part, you can read the slide, we go over it already. Number one is about this viscosity of mixture, okay? Zach, you agree with that? That's the first one. Okay, we know how to do the analysis of, do the bottle test. There's no equation with that, okay? This equation, you got to write down, convert from API to gamma to API if you don't remember. Slide 11. So if I give you API gravity, and I want to know the density, that's a fact. Okay, you have to write that down. So that's the second equation. Alright, third equation, that is just conceptual thing. Okay, the amount of heat we need is kind of flow rate multiplied by specific capacity, not specific capacity, specific heat capacity and change in the temperature. Okay, and that's kind of derivation. So if we have 10% of water, that is the equation. If we have any kind of water cut, that is another equation. So we have 4 equations. Most likely, you will use that. Good?
And that's the 6.35 and 8.33 are constants?
Constant. Okay. For the grad student, maybe next semester, they need to know how to get that. For you, not very much. The derivation is there, but basically it's based on a certain assumption of density and specific heat capacity. So that equation tells the amount of heat that we need. Okay. So we have 4 equations. That's it. Just 4 equations. Do you like it? Just 4 equations. And next is about reading the chart. Reading the chart that we need to know, okay, if it is off the chart and we need to know BTU per hour, we divided it by 10. Read the chart normally, get the result, multiply it back by 10. Good? That's using the chart. With all those things, we can size the heater treater. There are more than one chart. The chart will be provided. Okay. So this time, this lecture, we're gonna talk more in detail how do we really size it. Okay. There are 2-3 more equations, just that. But right now, all those equations, anyone has any problem with that? Not much? We can do that, right? Use the chart, calculate the total heat. Okay, total heat required in this chart is depend on how much temperature we want to raise and the amount of water in that. Okay? And when you look at this chart and this equation, okay, flow rate, percent of water, delta T, give BTU per hour. So this equation should do something similar to this chart. You agree? So if your calculation is not the same as the chart, or the chart is not the same as that calculation far off, there's a problem with that. So now we have 2 methods to get BTU per hour of heater treater. Okay. Let's take a look at other requirements. So this is just how to use it. So I just show that, okay, I get that much and it's kind of matched to the value from the chart.
What was the other slide about?
This slide is about Q total of 60, no water, temperature raised by 60 Fahrenheit. Okay, so this is the BTU per hour, calculated from equation. So if I have 60 barrel per day, let's go back, 60 barrel per day, where is it? That's the 60 barrel per day, right? That is 60 barrel per day. I don't have any water, no water is that line. I stop there. And I want to raise the temperature of 60 Fahrenheit up. So I move to the left, I stop over there, I go up, I get 20,000 something. Okay. Oh, we have time for question for sure. I did the same thing with the equation. I get the same thing. Okay, question.
Yeah, on the previous slide,
What's your name, sir?
Alex.
Alex? Okay, previous slide, this slide.
No, it's with an X. Alex.
Alex with X.
On the previous slide, the W says that it's, what is it, or pound per hour for flow rate, but then you said it's water, so is it like the water flow rate? And then the capital Q is the, like the oil.
You see this flow rate? We start with that flow rate is the same as this flow rate. This is Q total.
So then what is that W?
The equation with, you see this equation?
Yep.
That one is not the same as that one. This one is just to understand the concept behind all this calculation. The actual equation that, so this equation is like the starting point that people use that and eventually do some derivation, do some math and get that.
So the variables change.
Previous one with W, that is the starting point. You don't really use it unless you want to derive this kind of equation or that kind of equation. This equation doesn't have W. You see that?
It does.
Oh, W over here, where's W?
It's actually right there.
Oh, WC. Oh, that is percent water cut. If we have 10%, WC will be 10. Okay, sorry about that. Is it good, everyone? Yes?
On the chart,
On the chart.
if the units, it says it's just barrels per day.
Barrel per day.
So we're just supposed to know that it starts at 1 on the left-hand side and not at, say, 10?
10 is over there.
What's
You see
that?
that? That is 10.
Right, so
And that is number 1.
why when it goes to 20, does it go back to 2?
Okay, let's take a look
I
at
get that that's 20.
let's take a look at the axis. That is number 1. You agree?
Yeah.
Next one is number 2.
Yeah.
And that one is 10.
All right.
Okay? This part doesn't have any confusion. The next thing when it says 2 over there is not really 2.
Right.
It's just because the space is limited. It's 20.
All right. So we're just supposed to.
So the way to read this chart is when it have just single digit number, it doesn't mean 2, 3, 4, 5. We need to look at this number too. And that thing is 1,000. Okay? Good? Question? Yes, sir.
Can we have all the charts that we would have on the test in advance? That way we can work with them on the homework and.
Maybe.
I don't think that's a bad request. You
It's not a bad request. I will think about it.
I mean, 70 of each chart.
Well, there's a lot of charts.
There's a lot of charts.
How to use each one in each different situation.
I promise you, the chart that pop up in the exam will be one of these charts that show in the class. But it's still a lot, right? It's still a lot. I'll try to do something to make sure. Okay. I'll try to make sure that it's straightforward enough. And if I can make it on time, I don't promise, okay, if I can do it on time, maybe you have the chance. If I just do like, when is the exam time? 5? If I do it in that morning, maybe you don't have anything. Okay? Alright, this is the proof that that equation gives the same thing that the chart gives us. Okay? And this whole thing that we do tell us BTU per hour. Okay? Alright. Israel. That's Israel. Israel. How come we have just 60 barrels per day? Is that too small? What is that exactly 60 barrels per day? When we say emulsion 60 barrels per day.
I'm sorry, can you repeat the question?
What is that 60 barrels per day?
So it's a rate.
Flow rate of what? Emulsion, of course.
Yeah.
Where is that emulsion?
And,
Inside the heater treater? Could be. It is the flow rate. Incoming emulsion to the heater treater. We have heater treater. And the incoming stream is 60 barrels per day. That's what it is. Do we produce 60 barrels per day of oil? Okay. Why should it be just that small? Is that because we use something to separate water first, Israel?
Yes.
What is that?
It's for pre-water knockout.
Pre-water knockout, yes. Remember one thing that whenever we have this, we should remove all the water first. So even though the line over here says water in emulsion 100%, you see that line? 100%. We won't use that. If we use that, this means we need some kind of free water knockout. 80%, 60%, that's too much. Even though it's available in the chart, don't do that. Try to separate water out first. Good? Alright. Okay, the next step is, let's take a look at the characteristic. Okay. Temperature heating guideline. If we have loose emulsion means it separates relatively quick. Okay. Moderate emulsion means it takes some more time to separate it. Tight emulsion means it's very difficult to separate. Okay. Everyone do the sign-up sheet? Yes? Who did do it? Give it to him, please. Okay. Did you come here? A little bit. Is it more than 5 minutes? Okay, just have him sign it. If it is tight emulsion, depending on what kind of heater treater, okay? If we use a regular heater treater, conventional model, if it's very tight emulsion, we have to go hot. You see that? But if we have down flow treater, we can go a little bit less hot. Why is that? So what's your name who just come?
Devin.
Devin? Why is that? For down flow model, how can we use less temperature?
Sure, because the way it's designed.
The way design, of course. Let's take a look. Conventional one,
Did you go forward or backwards in the slides to get there?
backward.
It's just hard when you go back and forth. To
Yeah,
know which way
sorry
you're
about
going,
that.
I'm trying to write.
So one of them has this kind of baffle. One of them doesn't have any of that. You see? So the difference in the design cause different kind of separation. If you have a good design, Silver suggests that okay, we don't need to have it that hot. So pay a little bit extra. Okay, now I go forward. Pay a little bit extra to do the downflow model. We can do a little bit less heat. Okay, less heat is good in terms of not just use less energy, but this also means that it's safer in the operation. It's not hot, so it's safer, and we will have more liquid coming out. Okay. Of course, the set temperature, sometimes this is one of the criteria. Another thing that we have to look at is the reed vapor pressure, that 9.5 psi G at 100 F. You remember that? Okay. Alright, loose emulsion, we hit it about that much, or if it's downflow model, we have it that much. What about this gun barrel tank? Can we do heating in gun barrel tank?
Yeah, apparently.
Yes, we can do it. And gun barrel tank can be used to separate emulsion too. Okay. It takes less temperature, even though this is loose emulsion. Conventional treater take that much. Gun barrel take less emulsion, less temperature. Devin, next to you, what's your name? Caesar, why is that? Why gun barrel require less temperature if we want to do heating in gun barrel? What do you think? Next, what's your name? What do you think, Stephanie?
Bigger.
Because it's bigger, correct. Camera is bigger. It have more volume, so more settling volume is have more retention time to begin with. We don't need to heat much and it stay there a long time, okay? So this recommendation, I need to print it for you and put in there because you probably cannot memorize all that. There are many more numbers to memorize. Alright. Heater treater is, normal heater treater is direct heating equipment. It's not indirect, okay? So for direct heating, there's a model number, the size, firebox rating, working pressure, okay? Inlet and outlet. Okay, if I have heater treater set at 50 psi, 50 psi, and oil from heater treater go directly to oil tank. Okay, let's try on this side. What's your name? Jesse? What is the pressure rating for the oil tank? Did you go to field trip? Did you write it down? What's that? Okay, next to you, what's your name, sir? Ben, how much is the pressure rating for the oil tank? 1 psi G. This is just 1. So how come can we flow from 50 to 1? Ben, let me help on. How can we flow from 50 psi to 1 psi? Does it cause a problem? No problem? Okay, next to you, what's your name, ma'am? Jasmine. Is it Jasmine? Okay. How can we flow from 50 psi to 1 psi? Okay, what's your name? Emily. How can we do that? Okay, of course. This is oil line. Does it have back pressure regulator? On the oil line, you remember what's the name? Back pressure regulator, Kimray valve. The red thing on the bottom look like that, and have diaphragm in the middle. Do we have Kimray valve over there? No back pressure regulator over there. So what type of valve is over there, Emily? You didn't go to the field trip. Is it my group? Oh my God. So over there we have dump valve. You think? You remember that dump valve? Okay, dump valve just open or close. It doesn't control the pressure, anything. How can we go from 50 to 1? Linan?
There's a pressure regulator in the line or a choke or something that.
There's a choke, pressure regulator, are you sure about that? What do you mean? We don't have anything, is that okay?
We don't have anything?
We just have the dump valve that open and close. Is that okay? Sure? Why not? Okay, maybe Mr. Bula didn't emphasize this enough. At home, we have he talked about it already, okay? I have to talk about it again. At home, we have a water valve. What is the pressure inside that water valve? About how much? 40? 30, 40? So when I open it, it comes to a tree. A tree. Okay, then what happened? Nothing, it just flows. If the pressure inside is a lot, but I open the valve just a little bit, so it comes out just a little bit. You see what I'm saying? So if I have a 40 psi garden hose, I open the valve just a little bit. Water come out just a little bit. You see what I'm saying? If I open more, water come out more. If the pressure inside is not 40 psi, but nothing, maybe 5 psi, I open all the way, it flow very slow. You see what I'm saying? So there's nothing wrong to go from 50 to 1. Okay?
But isn't that using a valve as a pressure regulator or as a choke, which they're not meant to do?
It's similar to the garden hose. When I open the valve, it's kind of gate valve. Right? When I open this valve in the water hose, the opening go up a little bit. When we have just a little bit of opening, there's a lot of pressure drop across that. So that small opening by itself reduce the pressure quite a lot. Okay? Good? But if I open it all the way, it goes from 40 to 0 psi. Water just comes straight to a tree, just that. Maybe a little bit further away, just that. Alright. Inlet size, drain size, total volume, approximate ship weight. We have all that, okay? The thing that we need to pay attention is this part. BTU per hour and working pressure. Alright, if I have heater trigger of working pressure of 50 psi, Arif, how do I make that happen? Working pressure of 50 psi. I have heater trigger, okay, 50 psi, and before heater trigger will be free water, knock out. Okay, that's stay before heater trigger. How do I make heater trigger stay at 50 psi, Arif?
The level, particularly the level of coming in, this side fast level that we can get this down.
Okay, let me repeat the question. The question is, how do I maintain 50 psi or maybe 45 psi inside heater treater? How do I do that? How do I maintain 50 psi in there? Who want to have a rib? Who want to have a rib? What's your name, sir?
Sean,
Sean?
is it the pressure release valve to keep the pressure down?
Pressure relief valve. Stay over there on the top. Okay.
No, it's on the side. Or
So pressure relief valve that have the green elbow and have the hole over there. Is that what you're talking about? Okay. Who else want to have it? Yes, sir. What's your name? Trevor. What do you think? How do we keep the pressure inside heater receiver to be 50?
oil dump valve?
Okay. Next. Who else? Back pressure valve. What color is that in the field trip? What color is that?
Blue color, I don't know the color it is.
Did you go? It's red. It's red. It's red. The valve there, when it's red, is always red. So the back pressure regulator located at the outlet of the gas phase. What's your name? Did you just answer it correctly? Yeah?
Jonah.
John?
Jonah.
Jonah. So that is Kimber valve, back pressure regulator. Because of that keep pressure in there to be 50. Okay. If we lose it a little bit more, maybe it go down to 45, 40 or something. On the top there's a way we can adjust the spring. So that thing control the pressure inside the heater treater. Okay. And pressure relief valve, of course, we need that. So in the case that something wrong happened and a lot of pressure come out to the tank doesn't explode, gas just come out on the top. Okay? Good? Alright. Coil area, delta T thing. At the end we have what? Indirect heating method. Okay? If we have very corrosive material, okay, a lot of H2S, we may not be able to do direct heating. We may have to do indirect heating. Okay, if we do indirect heating, the normal one is direct heating. Every normal heater treater that you see is a direct heating. It's just like the one that we see in the field trip. So indirect heating is not that common. People use it when the material is very corrosive. Okay, if it's sour, very sour gas or something, have some sour gas. So the way to do the indirect heating calculation is the same as a line heater. You like that? It's like a line heater. We need a coil area calculation. Coil area. So normally we don't do this calculation. All right? You understand that? But sometimes when we use indirect heating, we calculate coil area from this. A is a coil area, Q is BTU per hour, U is the film coefficient, T sub F is the lock-in temperature. Okay. U is the overall film coefficient. Q come from the previous chart. I mean this chart. That is where Q come from. Or you may use that equation. That is where Q come from.
That's the chart that was back a bunch of slides.
Yeah, the chart that have to multiply 10. Yes, I go back.
Yeah. It's just hard to, when you go back and forth, it's hard to keep track of where you're going.
Okay, I'll try to go back.
Backwards or forwards.
U value come from another chart, similar to the chart of line heater. Okay? T sub M is a log mean temperature. You need to write that formula down for the log mean temperature calculation because that is used in line heater already. So this part, when we have indirect heating, which normally we don't, we do okay, log mean temperature difference from that, U value from another chart. So this is the equation that do more accurate U value calculation. Okay, it's kind of weighted average. U value of oil and U value of water and multiply by the fraction to do the weighted average. Okay, U value come from this chart. Water flow rate. You see water flow rate in the pipe. If we flow fast, depending on what type of pipe we use, then we get U value. So this looks just like heater treater. Line heater. Normally heater treater doesn't operate this way. Okay, this is a little bit more. Overall film coefficient for indirect heater. Indirect heater include line heater and some type of heater treater, which normally we don't use unless it's corrosive. Okay, and that's the diagram. We heat water first, and there's a coil coming in, similar to line heater. Do we normally use this thing for heater treater? No. Okay. No, don't use this. It's just to confuse you. In normal case, where it's not corrosive, we use this thing. HH, not IH model. IH model is indirect heating. Okay, good? That's more like for line heater. Alright, gravity separation is another thing that we have to look at in the heater treater. The equation derivation based on Stokes law and buoyancy. At the end, we get that equation. So that equation, you're familiar with it, right? We already talked about it. Make sure you know how to put the number in, okay? That's what we test you on. Fill unit, SI unit, okay? Alright, settling thing has to do with internal part of the line heater. Most of the time, we can use the gas capacity equation or liquid capacity equation from that horizontal separator or vertical separator directly. Okay, so this equation will be similar to the horizontal separator for the gas capacity equation. Okay, it depends on how much is the volume inside, so we can approximate this to be something similar to horizontal separator. We don't. This is just for your information that we can do detailed calculation inside to find out what size do we need for the line heater. Okay, so the size that we need for the line heater basically based on the settling volume, okay, retention time of the emulsion. Alright, so for horizontal line heater, that is the equation used to do the approximation. Okay. F typically we just set it equal to 1 if it's just a regular heater treater. The derivation of this is the same as horizontal separator. Okay. Vertical one, we have another formula. So this thing will exactly tell us, do we have big enough heater treater or not. So if I have vertical heater treater, I say, okay, we have just regular heater treater. Okay, the treater has a spreader or collector. We know the difference in the specific gravity. That thing has to be determined at the temperature of heater treater. Okay, we know viscosity of oil phase. We know the oil flow rate, Q sub O. That's the image. Q sub O we put in barrel per day. Okay, we know all that. We know droplet size. Put it in, I can tell the diameter of heater treater. Good. That's the equation to check if we have big enough heater treater or not. Okay. The treater sizing, we may use it for gun barrel too. Okay. This is for vertical one, this is horizontal one, and the unit spelled out over there. The derivation is based on terminal velocity equation. Okay, so we have gun barrel equation. This tells us barrel oil per day, C value from table 1. You will see that there are kind of two ways of doing it. Okay, this is like pure theory. Theoretical approach give us those equations. Okay, that is theoretical approach. From the vendor, then we have their chart and everything. Okay, we use table 1. That's table 1. Table 1. So table 1 give me the C value, droplet size. If we have some free water inside the emulsion, so if it's just emulsion with some free water, that means it's not really very tight, or it's loose emulsion, moderate emulsion. So I have droplet diameter over here. Put it there. I know the viscosity. Then I know the volumetric flow rate. Then I can calculate the diameter. Why do we have two kind of equation? Which one to use? Is it confused?
Always.
Always confused. Okay. If we buy it from the vendor, we use vendor recommendation equation. We use these two equations. Good. The vendor itself may use this kind of more accurate calculation to find out if the chart that they made for the customer is correct or not. Typically, we use these two. Okay. But if we don't have any test, so this requires C value. You see that C value? C value is, if we have loose emulsion, C value will be that much. Tight emulsion, C value will be that much. If we use free water knockout, use that much is for C value. Where's the C value coming from? Test, experiment, right? It requires a test. If we don't have any test done, we don't have this equation, and the only thing that we can do maybe is, okay, assume f equal to 1. Both of them should give similar answer. Okay, use just one out of those is okay. I recommend this form because it's easier. Okay, this one that derived based on the settling volume or something is a little bit more complicated, but it can be used if you don't have any test done. But look, when we use this equation, every time we have d sub m and d sub m, how do I know d sub m, the sum, if I don't do any test? But the vendor version tell, okay, this is how much for the droplet size. So try both versions, and maybe you tell me, do you get similar answer or not? It should be similar range. If we have to answer, which one do we go with? This one, because we buy it from, okay, if you buy from other vendor, you may use other chart, but if, depending on where you buy it from, if you buy it from that company, we use that chart for the first recommendation. Good? The chart is typically given from the vendor for us to size it. We have downflow treater model. So it says over here, downflow emulsion treater. So downflow can heat less than the conventional one, so it's better. Okay, of course, maybe more expensive. It has a concern with API gravity. 46 degree, 40 degree. So we need to know API gravity. Heater temperature, how much is the heater temperature? We need to know the specific gravity of water. How much salt do we have in water? We go up here, move this way, and we need to tell if we have the loose emulsion, moderate emulsion, or very tight emulsion, then we go here. And this thing will tell, oh, do we use this size, or that size? Depending on the size, we can accommodate different kind of flow rate. So this tell me, okay, let's say I have 1,000 barrels per day, and I try to use that flow model. So after the free water knock out, I expect about that much of emulsion of liquid phase coming in, okay? About 1,000 barrels. And I know that, okay, if I have that much API gravity, it's moderate emulsion. If I use this size, maybe I can get it right at 1,000 API, right at 1,000 barrels per day. So if I use 8 by 12, okay, that model will do 1,000 barrels per day.
That's just oil or total fluid?
It wrote over there oil, but when we actually do the calculation, to be a little bit more conservative, we may put the total fluid, because when you look at this chart, there's no place that we put water cut in it. There's a water cut. How much water do we have? And when we size, the reason that we should use a total one, because this, when we size the heater treater, if the total volume coming in is a lot, we need bigger separator to have more retention time, right? So that has to be based on the total volume. So look at this one. If we go right at 1,000, maybe I have 1,050 barrels per day, okay, of emulsion. But can I use this size? Yes, maybe. If I use that size, I may heat it a little bit more. So if I heat it a little bit more, maybe I can take more incoming liquid. Good? So I can heat it a little bit more. So this chart tells us, okay, they say oil capacity, like liquid capacity that they take. Okay, this is a larger version. Okay, how do they do that? Retention time calculation. Okay, W equal to 1440 something. All right, retention time inside. Retention time has to be based on a total flow rate. Okay, total flow rate that go inside. Gun barrel